This presentation is on the topic of thermodynamics. Thermo still referring to heat and energy, and dynamics now is the motion of that heat and energy, or how it affects the particles of the system and the surroundings. So this is a little bit of a different order than the book, but I want to start by talking about free energy. When a system changes energy, it can be related to two factors. One is that heat change, that energy change, which we refer to as the enthalpy. And the other change is the positional or motion change. The positional change is talking about the particles and their position related to each other, their spacing between them, the organization of them within a molecule. And the other motion change is referring to their freedom of motion, their ability to move. Okay, where the heat change is referring to the speed at which they are moving. The motion change is referring to whether or not they actually have the ability to move. So the heat change is what we call the enthalpy change. The positional and motion change is what we call entropy. When a process occurs, there is a total amount of energy transferred, and that's what we refer to as the free energy. It's the total amount of energy available to do work. So that's the definition of free energy. If the total free energy change is negative, then the process can occur on its own without outside interference, and this is what we refer to as a spontaneous process. If the total free energy change is positive, then the reaction can still occur, but it requires outside influences to help it occur. So the idea of spontaneity is that if a process is spontaneous in one direction, then it's going to be non-spontaneous in the reverse direction, which should make sense. If it's going to happen automatically in one direction, then the other way it's going to need help. Thermodynamic properties tell us nothing about the rate at which the reaction occurs, however. There are reactions that are very, very favored to occur thermodynamically, but their reaction rate means that it could take hundreds or thousands of years to actually occur. Reversible processes are processes that can be restored to their original state exactly by reversing the process. So you don't have to do, or you can't do anything different to the substances in order to get it back to its original state. So reversible process can go back exactly the way it came. All spontaneous reactions are irreversible since it takes work from the surroundings to get it back. Because if it's spontaneous in the forward direction, then it's non-spontaneous in the reverse direction, which means the outside surroundings has to be able to add energy to the system, and therefore it's not going to go back the way it came. Entropy can be looked at as either the randomness or the freedom of motion of the particles. It's a state function, so the entropy change can be determined from initial and final states. All right, so we're looking at how randomly distributed particles are. If they're more confined to their volume, they're going to have less entropy. If they are not allowed to move, like in a solid, they're going to have less entropy than they would as a gas. So that's what we're looking at with entropy. Particles that have more locations that they can occupy and more freedom to move have increasing entropy. So if you increase the volume of space, there's more possible locations that molecules can occupy within that space. So that gives them more entropy. And if they're not close to each other and they're not attracted to each other and they're not bound to each other, then that will give them the ability to have a higher entropy. This is clearest in phase changes, since the entropy increases as you go from a solid to a liquid to a gas, because you're giving them an additional freedom of motion. Or when you dissolve a solid and make it a solution out of it, now the ions are free to move, where before they were bound together. If you have larger molecules, too, you also have increasing entropy, because those molecules can have more ways of vibrating and moving, where the atoms inside are actually moving on the bonds and shifting. So when delta G is negative, and G is that free energy, that means there's a release of energy. That energy goes into the universe, raising the randomness of the universe. So when the reaction itself releases that free energy, then the universe is going to have more energy in it, which is going to randomize it more. So you're going to increase the entropy of the universe. If the process is reversible, though, then there is no net change to the universe, so your free energy change is zero. So if you have a reversible process, then there's no net energy difference with the universe, and so then your free energy, your delta G, is zero. The second law of thermodynamics states that the entropy of the universe is unchanged in a reversible process and increases for an irreversible process. So you can only keep the entropy of the universe unchanged or increase it. There is no way to decrease the entropy of the universe. When we have a situation where we have a reversible process that happens at a specific temperature, we call that an isothermal process. Phase changes are a perfect example of an isothermal process because the temperature isn't changing and you can go back and forth between the states because they're at equilibrium. All the energy going into the system to melt the ice, if you want to use that as an example, can be returned to the surroundings exactly the same as it entered without any temperature changes at all. So entropy changes for the change of state can then be calculated for any temperature. The third law of thermodynamics is that the only time you have substances that have zero entropy is when they are at 0 Kelvin. So if the entropy change is calculated for the reversible reaction and it relates to the heat change, so S is the symbol that we use for entropy, so the change in entropy is equal to the heat of the reversible reaction divided by the temperature. Any heat lost by the reaction goes into the surroundings, increasing the entropy of the surroundings. So what that means is that your delta H of the system over the temperature, and notice there's a negative sign there because your system is releasing it, will cause a change in the entropy of the surroundings. And at constant temperature and pressure, the entropy of the surroundings plus the entropy of the system will equal the entropy of the universe. So when we substitute the delta S for the surroundings in, we get negative delta H over T of the system plus the delta S of the system, or the entropy of the system, will equal the change in entropy of the universe. If we multiply everything by negative T, we end up with minus T delta S of the universe equals the delta H of the system minus T delta S of the system. And that T delta S of the universe is going to be what we're going to consider to be the free energy, because we don't have to worry about the universe and the surroundings if we look at the free energy change of the system. So delta G equals delta H minus T delta S is the equation that we use that relates free energy to enthalpy and entropy. So at what value of delta G is delta S of the universe greater than 0 as spontaneous? Well, if the delta S of the universe is positive, and that's equal to delta G when you multiply the delta S of the universe by negative T, that means that the delta S of the universe is positive when delta G is negative. And so that's how you know that a reaction is spontaneous, is when your delta G is negative. So here, if we have, using the equation, we know that delta G is negative in the first one. If delta G is negative, then your delta H will probably be negative. You'll have a exothermic reaction. Your delta S will probably be positive. So whenever you have a delta H that's negative and a delta S that's positive, then delta G will always be negative at every temperature. If you have a delta H that's positive, meaning it's endothermic, you have to put energy in, and your entropy is negative, which means that your particles are becoming less random, then your delta G is positive all the time, which means that it'll always be non-spontaneous. Doesn't want to happen, so it requires outside influences to do that. Which, by the way, does not violate the second law of thermodynamics, because in order to put that energy into the reaction, you have to do something outside of that to produce that energy, which is going to make the universe more random. So no matter what, you can't violate the second law, even though you're technically violating it on this reaction. If you have a enthalpy change that's negative, so you have an exothermic reaction, but your entropy is also negative, meaning that you're less random, that means your delta G can be positive or negative. If you have a low temperature, then your entropy doesn't make that big of a difference on your delta G, so you could still have a negative delta G. If you have a high temperature, though, then that entropy is going to be able to outweigh the enthalpy effect, and therefore you will have a non-spontaneous reaction. If you have a endothermic reaction and you have positive entropy, meaning that it's more random, then your delta G can also be positive or negative. And again, it depends on whether the entropy is having a greater effect on the free energy than the enthalpy or not. And so that's only going to happen at high temperatures where the negative T delta S will be greater than the delta H. When the free energy is at its lowest point, we say that the reaction then is at equilibrium, because that's where you're going to have your reversible processes. Any reaction that is not at equilibrium will be spontaneous and will decrease the free energy to reach that equilibrium point. At equilibrium, then, your delta G is 0 because they're at equilibrium, so it's a reversible process. So you can rearrange the equation and find that the delta H equals T delta S. So you can use this to determine, based on the heat change, where your melting point and boiling point is and things like that. So you just plug in your delta H and your delta S, and you can figure out your temperature necessary for the phase change to occur. The equation that relates delta G to your equilibrium constant is delta G equals minus RT natural log of K, where R is the gas constant, which is the 8.314 joules per mole Kelvin. It's kilopascal liters, which is joules. And then your K will be your K from equilibrium expression. When you're not at equilibrium, though, the equation looks like this, where you have delta G equals delta G standard, so you'd have to look up that value, minus RT natural log of Q, where you plug in your reaction quotient. So if you look at it graphically, that lowest point of your free energy is where it's at equilibrium. So if your Q is less than K, you're going to have a spontaneous reaction heading towards that equilibrium point. If Q is greater than K, you're going to have a spontaneous reaction that, again, is taking it towards that equilibrium point and that lowest free energy. Delta G and delta S are also state functions, so we can use Hess's law ideas to calculate both delta G and delta S if we know other reactions. And in addition to that, they can also be calculated using the standard molar entropies and standard free energy of formations. And these are the values that you would look up in the back of your textbook. And you just do the same thing you did for the enthalpy changes, where you do products minus reactants. So you can do the entropy of all the products minus the entropy of all the reactants to get the delta S. So you look at the free energy of all your products and subtract from that the free energy of all your reactants. And then you will get your delta G for the reaction. We will cover a lot more of this in a lot more detail and answer lots of questions on this in class.